Okay, so we will continue the study of LP spaces, and depending on the time we may go to some new topics, but I would like to give some examples which will make you familiar with the LP spaces we are dealing with. So, we have been doing everything in the abstract settings. Let us look at some very concrete situations where we have the Lebesgue measure or the counting measure or some of the measures which you are familiar with, and see how the results we have done so far takes place or manifests in this concrete situations, because some of this will be you will have to use it later on when you deal with LP spaces on the real line or Rn in general. Okay, so let us start. So, we remember, so let us immediately recall some of the settings. So, we had this measure space as usual, and we looked at LP mu, which was a complete metric space, okay. And if X was locally compact Hausdorff space and we had the measure and the sigma algebra as in Riesz representation theorem, right. So, in particular all the abstract results which we proved would be applicable to the concrete situation when X is Rn and mu is the Lebesgue measure, right. So, the measure the sigma algebra M would be the Lebesgue sigma algebra of Rn. Okay. Then we know that Cc of X is dense in LP of mu, right, but this remember is true only for p strictly less than infinity. Okay. L infinity it will not be true, we will see some examples soon. So, let us now we are going to look at some really concrete situations. Okay. So, we will start with a simpler space. So, let us take X to be this. So, examples. So, let us take X to be 1, 2, 3 etc. So, this is the set of positive integers, okay, and we should have a sigma algebra F. So, this is just 2 to the x, the power set, and mu the counting measure, So, we can consider X with the discrete topology. So, what is the discrete topology? All sets are open, right, discrete metric, all sets are open. So, what are compact sets here? Compact subsets of X are finite sets, right, no infinite set is compact. So, these are finite sets. So, in particular when I look at well, it is discrete topology. So, any function is continuous, right, any function f from X to the complex plane is continuous. Well, how does the function look like? Any function f is simply a sequence, right. So, this is just f1, f2, f3 etc., right. We will write it as an infinite tuple. Okay. So, now if I look at LP spaces, okay, so let us look at LP of X, we have this f and the counting measure mu. How does it look like? Well, you look at any function on X which is in LP. So, I want the integral of f modulus of that to the p d mu to be finite, okay, but f is a sequence. So, I can write f as, let us take a1, a2, a3 etc., right. What does that mean? This means that f of j equal to aj, right, j equal to 1, 2, 3 and so on. So, that would be the function which is identified with an infinite tuple. So, what is this quantity in this situation? This would be integral over x mod f to the p d mu is simply a summation, right. The integral with respect to a counting measure is always a summation. So, this is j equal to 1 to infinity mod aj to the p. So, I want this to be finite, correct. So, this is the sequence space. So, we will denote it by, so this is a sequence space, this is a space of sequences and will be denoted by small LP. Okay. So, small LP of n, right, because n is our space. So, this is simply, we again forget the topology and all that, right, because everything is continuous, right. So, all I have to do is to look at sequences A1, A2, A3 etc., right, with the property that summation j equal to 1 to infinity mod aj to the p, right, integral d mu is just this, this is finite. So, this will make sense for 1 less than to p strictly less than infinity. I will come to p infinity soon, but what is the norm here? So, norm of a function is a tuple, right. So, I look at a1, a2 etc., well a3 etc., infinite tuple, I look at the LP norm. Well, this is simply the integral of the function which is mod aj to the p, right, d mu to the 1 by p, right. So, this would be the norm. So, this is a perfect generalization of what is happening in Rn or Cn, right. You have seen this for finite dimensional spaces, and now we look at infinite tuples. Okay. So, this is the norm. Well, what is the norm for infinity? So, p equal to infinity, we will be looking at L infinity of n. What is this? This is look at infinite tuples a1, a2 etc., such that the L infinity norm of this is finite. So, what is the L infinity norm? We will see that. Okay. This has to be finite. What is the L infinity norm? So, L infinity, let us recall that if I have a function f from x to let us say c or wherever it is, the L infinity norm of f was, you look at infimum of all those m such that mod f x mod f is less than or equal to m almost everywhere, right. But see, almost everywhere condition says there are sets of measure 0, but in this in the situation where it is the counting measure, there are no sets of measure 0 except the empty set. So, because of that, this is simply the supremum of f, right. So, this is nothing but supremum over j mod aj. Okay. So, these are bounded sequences. So, these are bounded complex sequences. So, that is your L infinity and this is LP. Okay. So, now let us look at the result that CCX is dense in LP, right. So, this was a result we proved on less than to p less than infinity. Let us apply that. So, what does CCX mean? Compact sets are finite sets, right, in n, because we have a discrete topology. So, in n they are simply finite sets. Any function is continuous and the support is compact. What does that mean? So, CCX is simply all those tuples which are 0 except on a set of finite measure. So, this is simply all finite sequences, right. What does that mean? So, I will write this down. This is simply A1, A2 etc., all those tuples such that for every A1, A2 this tuple there exists some n, well the n can change depending on the tuple such that Aj is 0 for every j greater than or equal to n. Okay. So, you keep writing A1, A2, A3 etc., An and then it is 0 0 0 0. So, eventually 0 sequences, right, eventually 0 sequences. So, that is what we mean by a finite sequence and that forms the continuous functions with compact support, because compact support meaning there are only finitely many non-zero terms in the sequence, everything else will have to be 0 and that is dense. that we know by theorem, but it is also easy to see, right. So, let us try to do that. So, let us take a function in LP in this setup. So, let us say this is in LP. So, I know that summation mod A j equal to 1 to infinity to the p with to the 1 by p, this is the norm, right, this is finite. How will I approximate this with a finite sequence? So, given epsilon, I want to say that I can get a finite sequence which approximate this. So, let us see. So, given epsilon positive, I know this is a convergence sequence. So, choose capital N, so that the tail of the series j equal to n plus 1 to infinity mod a j to the p to the 1 by p is less than epsilon, that is possible, right, because it is a convergence sequence. So, now it is clear which function approximates this, right. So, consider, so let us call this function A, consider the function B, that is A1, A2 etcetera A3, An and then 0 0 0 0. So, you put zeros at the end. This is of course in LP, okay. It is a finite sequence and it is a continuous function with compact support on n. What can you say about the norm of A minus B? Well, if I look at the LP norm, because the first n terms are same. So, when I subtract they will go and I have zeros here and the aj's, right. So, this will be summation mod aj to the p j equal to n plus 1 to infinity to the 1 by p, and so forth. This is less than epsilon, right, because of this, that is how we have started. So, B approximates A. So, that is why these things are dense. Well, there are more properties of LP which you should know, and you here you will immediately see that it is not true in L infinity. So, consider L infinity, consider L infinity of n. Let us take a sequence 1 1 1 1 1. Okay. So, let us say A equal to 1 1 1 1 etcetera, all ones. Okay. So, it is a bounded sequence and the L infinity norm of A is equal to 1. Can I approximate this with any finite sequence? Can you approximate A by any finite sequence? Because those are the compactly supported continuous functions, right. So, I want to try and see if I can approximate A with any finite sequence. So, let B be a finite sequence. So, this would be B1, B2, B3 etcetera, and there is some n for which Bn exists and then you have 0, right, finite sequences. So, if I look at L infinity norm of A minus B, what do I get? Well, so I will get in the first term A minus B would be 1 minus B1, then 1 minus B2, 1 minus B3 etcetera 1 minus Bn. So, these Bn's could be 1, so that all I get 0. But what happens next? I have 1's infinitely many terms and from here I have only zeros. So, I will have 1 minus 0 1 minus 0 which will give me 1 1 1 and so on. So, when I take the maximum, right, what is the L infinity norm? I have to take the maximum of this, but I have 1's here already. So, the maximum will be greater than or equal to 1, right. So, no finite sequence can approximate. So, if I take epsilon smaller than 1, there is no way the finite sequence will converge to A. So, that means CCX is not dense in L infinity, okay, in this case, right, because we are looking at. So, maybe I should write CCX is finite sequences, the collection of finite sequences not dense in L infinity of n. Okay. So, you can define similar L infinity sequence spaces, L infinity LP of Z and so on. Okay. So, try these with LP of Z. Okay. You can also look at some set X, okay, countable or uncountable, countable, uncountable, okay, and mu counting measure, and you can consider LP of mu, okay, or LP of x, that, or LP of x, I mean whatever notation you want, and you do the same and you will see finite sequences will not be dense, and these spaces will have certain properties. So, let me give some exercises so that you are familiar with these spaces. LP of n is contained in LQ of n if p is less than q. So, everything is between 1 and infinity. Okay. That is not difficult to see. So, the one thing to note is that if I take a sequence A1, A2, A3 etc. in LP, then it is already in L infinity, because it is the convergence sequence. So, the nth term has to go to 0. So, it is bounded. Okay. So, if you use that, this will immediately follow. Okay. And the inequality and the containment is strict. Okay. Containment is strict. What does mean? What does that mean? There exists a sequence A in LQ which is not in LP. Okay. That is easy to construct. Okay. So, now let us look at another example. So, I have, let us take the space X to be equal to 0 1, closed interval 0 1, that is a compact Hausdorff space, right. So, in particular all the theorems we know will be applicable. Mu is the Lebesgue measure. So, this is the Lebesgue measure restricted to 0 1, right. So, we know what this is, okay. And the sigma algebra is of course the Lebesgue sigma algebra of 0 1, right. You intersect every Lebesgue set with 0 1, you will get a Lebesgue sigma algebra of 0. So, what is LP? So, we can look at LP of 0 1. LP of 0 1 is by, so this is just the notation. So, this is just 0 1 script f and the measure mu. Okay. So, we will not when we do not write the sigma algebra and the measure, we assume that it is the Lebesgue sigma algebra and the Lebesgue measure. Well, what sort of a space is this? Well, this is quite nice. First of all, you can see continuous functions on 0 1, they are contained in LP of 0 1, right, and they are dense. Okay. It is dense for p strictly less than infinity. Again, for continuity reasons, if this was dense in L infinity, everything in L infinity will be continuous. Okay. So, maybe that is an easy exercise. Okay. See, 0 1 is not dense in L infinity of 0 1. So, L infinity of 0 1 will be all those functions which are defined on 0 1 essentially bounded, right. So, this is not with respect to L infinity norm. Okay. So, for example, you can take indicator of 0 half, okay, prove that, okay, well, prove that there exists no continuous function f which is equal to indicator of 0 half almost everywhere. First of all, that we do that, and if C01 was dense, this will lead to a contradiction, okay, because you will be approximating chi 0 half with any with continuous functions in the L infinity norm. So, the limit will be continuous, but this is not a continuous function almost. This cannot be a continuous function at all, in the sense that the, remember these are equivalence classes. What this means is, if I look at the equivalence class of this indicator function, okay, this equivalence class has no continuous function in it, okay, that is the meaning, right. So, if you justify this, then you know that. Well, so in the case of small LP, which is the sequence spaces, we had certain containments, right. So, we will see that that is true in this case as well. Okay. So, exercise again, prove that LP of 0 1 contains LQ of 0 1 if P is less than Q. So, here it goes the other way, that is not very surprising, because the spaces are different. So, here when we had this inequality, the containment was in this direction, but here it is just the opposite. That is because the measure is finite. Well, how will one prove these things? So, you need to realize that 0 1 has finite measure, right. 0 1, the measure of 0 1 is 1, which is finite. Because of this, constant functions are in LP. Constant functions are in LP, because if I take a constant function and take the pth power, that is still a constant that comes out, and measure of 0 1 will come, that is 1. So, this is trivial. Then you can apply Holder's inequality. So, if I look at something in LQ, so I am looking at, and I want to show it is here, right. So, I look at mod f to the p, and I can look at mod f to the p into 1 over 0 1, right, and apply Holder's inequality. So, I will get two things. You want to make sure that these two are finite, okay, that is all you need to do. So, apply Holder's inequality, Holder's inequality. In fact, if you can generalize this. So, let me give you another exercise here. Suppose f belongs to LP of 0 1 and f belongs to LQ of 0 1, well, not 0 1. So, let us go general. So, that I can write down a general thing. So, here I have x f mu, okay. So, I am not assuming anything on x yet. Suppose f belongs to LP of mu intersected with LQ of mu. So, that means it belongs to both of them, 1 less than to p, strictly less than q, strictly less than to infinity. Okay. So, I am not assuming anything on capital X. I do not know if it is a finite measure, I do not know if it is an infinite measure. Okay. But f belongs to 2 LPs, then it belongs to all the LP in between. Then prove that f belongs to LR of mu for every R between P and Q. Okay. So, if it belongs to 2 LPs, it will belong to all the LPs in between. Well, how will you do this? So, I have P and I have Q here, and R is somewhere in between. So, I can write R as lambda P plus 1 minus lambda Q, right, 0 less than or less, as a convex combination of Q. So, you should be reminded of certain convexity inequalities which we know. It is more or less like that. Well, Holder's inequality is what you can apply. So, you can, if I want to say that f belongs to LR, right. So, I will be looking at mod f to the R, and then I integrate over x, right. So, I can write this as mod f to the lambda p plus 1 minus lambda q, okay, which is mod f to the lambda p into mod f to the 1 minus lambda q. So, now I can apply Holder's inequality. So, for For Holder's inequality, remember I need conjugate exponents, right. So, you can take conjugate exponents p prime to be lambda, well not lambda because lambda is between 0 and 1, p prime to be 1 by lambda and q prime to be 1 by 1 minus lambda, right. Then I know 1 by p prime plus 1 by q prime equal to lambda plus 1 minus lambda equal to 1. So, these are conjugate exponents. So, apply Holder's inequality with those conjugate exponents here. You will actually prove that the LR norm is less than or equal to maximum of the LP norm of F times the LQ norm, maximum of LQ norm and LP norm. Okay. So, remember the R is between P and Q. Okay. All right. So, let us let's look at some more properties of LP spaces. So, we have C01 to be dense in LP, but it is not dense in L infinity because of this. All right. So, instead of looking at so let me give another exercise to sort of again be familiar with the LP spaces. Suppose I have x f mu and I look at the case mu of x is finite. So, this actually we did a special case of this when we looked at 0 1. So, whenever we have finite measure spaces we have the constant function 1 belonging to LP. So, you can assume you can use that to prove this in general. Okay. So, assume that mu of x is finite. So, this will imply that constant functions are in LP, right, all LP in fact. So, this tells me that if I look at LP of mu, so use 1 as a function, constant function and apply Holder's inequality. So, this will be contained in LQ mu if well the containment goes the other way because I want to keep writing P less than Q, P is less than Q less than to infinity. So, the space L1 is the biggest space, right. So, let's look at L1 of 0 1. So, now we are back to concrete situation 0 1. This of course will contain all LQ, right. For every q greater than 1. So, you can look at the union of them. So, this is a slightly tricky exercise, not too tricky. I look at all of them, okay, all LQs. Is the union equal to this? So, it is not. So, what you do is prove that construct a function f in L1 0 1 such that f is not in LP 0 1 for every p greater than 1. So, I will give you hints how to do this. So, well how will you get a function which is, so let's start with L2. Okay, I want a function f in L2 0 1 sorry f not in L2, but f is in L1. Okay. Well, the easiest way to do this is to keep the function 1 by x in mind. Okay. So, the function 1 by x has the property that, well, when x belongs to open 0 1 and does not matter what you define here, right, because the point has measure 0. So, it does not matter how you define the function in 2. So, if I look at 1 by x I know it is not in L1. Okay. Well, I know that if I look at 0 1 to 1 by x dx as the Lebesgue integral, this is infinity. Why is that? So, we have done this calculation before. You look at from 1 by n to 1 by x. this is a bounded continuous function. So, it is Riemann integrable, and so Lebesgue integral is equal to the Riemann integrable, and you compute this and let it go to infinity, right. So, you look at limit n going to infinity of this, you will get that this is infinity. By monotone convergence theorem, this cannot be in L1. So, if I modify this function to 1 by root x, okay. So, when x belongs to open interval 0 and 0 otherwise, right, then this is in L1, again by the same computation, right. But this is not in L2. So, let us call this g of x, okay, but g of x is not in L2. Why? So, integral of 0 1 g square dm, right, that is what we want to do. G is positive. So, mod g square is g square, but this is integral of 0 1 g square is 1 by x and dm, this is infinity. So, this is not in L2, okay, but it is in L1. So, you have got a function which is in L2, but not in L1. So, similarly you can get a function in, so for if I look at the function g of x equal to x to the minus 1 by p, p greater than, so fix p greater than 1, and this is when x belongs to open interval 0, closed interval closed at 1, 0 otherwise, then it is easy to see that g is in LP, g is in L1, 0 1. Okay, again just by root x, whatever you have done by root x, you can right, this is simply x to the minus 1 by 2. Okay. So, that is all we are doing here. It is instead of 2 we put a p. Okay, then g is in L1, but not in LP. Okay. So, now you choose a sequence Pn decreasing to 1 and consider x to the minus 1 by Pn. So, for each n you have this function, right. You can add appropriate constants and look at this function. So, you will see that this belongs to L1 if you choose ANs properly, okay, but not in LPn for every n, right, for any n. For any n, right. So, because Pn's decrease to 1, this will also imply that this does not belong to LP for 0 1 for any p, right, because of the containment we already have. Okay, so, that is an interesting exercise. Now, well, let us go to infinite measure spaces. So, let us look at another example. So, on Rn, okay. So, now we look at Rn. So, our space is Rn, we have the Lebesgue sigma algebra of Rn, we have the Lebesgue measure, okay, and we are looking at LP of Rn. Okay. Of course, Cc of Rn will be dense and so on. So, we have proved all this in general setup, but you can apply this here. So, if I look at a function, so let us look at the function f of x equal to 1 by mod x to the n plus 1, okay, where mod x is greater than or equal to 1, 0 otherwise. Okay. So, prove that f is in L1. So, prove that f belongs to L1 of Rn. Well, how would I prove this? So, let me give you some hints. One way of doing this would be using polar coordinates, which we have not introduced. So, we will do that at a later stage. So, right now what you do is, so it is 0 near 0, right. So, it works only for mod x greater than or equal to 1. So, you decompose Rn into all those points x such that 2 to the k is less than or equal to mod x less than 2 to the k plus 1, 2 to the k plus 1, okay, and I have 1 by mod x to the n plus 1. So, k will go from 0, 1, 2, 3 etc. So, if you decompose Rn like that, because k equal to 0 will give me 1 and out inside the unit ball there is no function. So, I need to look at only these ones. So, I can look at integral over Rn mod fx dmx, right. So, this is of course integral over mod x greater than or equal to 1, 1 by mod x to the n plus 1 dx, which I use this decomposition. So, this is equal to monotone convergence theorem will tell me that I can interchange the sum and the integral. So, summation k equal to 0 to infinity integral 2 to the k less than to mod x. So, this is a set 2 to the k plus 1. On this set I integrate mod x to the n plus 1 dx, right. So, I need to know if this will give me some quantity and I can sum up. Well, so it is pretty easy. So, on if I look at on this set on 2 to the k less than to mod x less than 2 to the k plus 1, 1 by mod x plus mod x to the n plus 1. So, that is a decreasing function, right. So, you put mod x to the smallest value, you will get the highest value of 1 by mod x to the n plus 1. So, this is less than 2 2 to the k. So, 2 to the minus k into n plus 1. Okay. So, I am putting the smallest value of mod x here and that will give me the highest value of this function, right, because it is decreasing. Okay. So, in this equality I can change this into, I can take the k equal to 0 to infinity 2 to the minus k n plus 1 outside, okay, and what remains is the measure of this set, right, 2 to the k less than to mod x less than 2 to the k plus 1. Okay. So, how will I compute the measure of this? So, this is where invariance properties of the Lebesgue measure will come in. So, measure of 2 to the k less than to mod x less than 2 to the k plus 1. Well, what is this? This is measure of 2 to the k times the set 1 less than or equal to mod x less than to 2, right. If I dilate, so remember the if I have a set A delta A, the dilation was multiplying everything by delta. So, this is simply the dilation, okay, dilation by 2 to the k, which is equal to, because it is we know the properties, it is just 2 to the n k times measure of some set that is fixed. Okay. So, now you apply it here. So, we will get, if you look at this, you will see that you have to look at this summation, which is summation 2 to the minus n plus 1 k, and I have these things 2 to the n k and measure of some set, some fixed set, that is a constant that comes out, and this will give me a series in 2 to the minus k equal to 0 to infinity, which is finite, times measure of some set. Okay, this is finite, and so this function is in L1, right. You can use the same proof. So, exercise, we will stop with this exercise, use the same proof, to show that the function f of x equal to 1 by mod x to the, we do not need n plus 1, n plus any epsilon will do, mod x greater than to 1, 0 when mod x is less than to 1 is in L1 of Rn if epsilon is positive. So, you take any epsilon. So, anything which decays faster than 1 by mod x to the n at infinity will be in L1. Okay, so we will stop here. So, in this session we did not look at any finer properties of the LP spaces, we looked at examples. So, this was to familiarize you with these spaces. The LP spaces on sequences will behave differently from LP spaces on sets of finite measure in terms of containment and so on. But if the space is nice in the sense of locally compact Hausdorff space etc., we have continuous functions which are dense, and there are functions. So, we restricted ourselves to Rn, and we saw that there are functions like 1 by mod x to the n plus 1 and so on which are in L1 and can be proved that they are in L1 etc., using invariance properties of the Lebesgue measure. We can do direct computations, and whenever we can, we remember that whenever a function is Riemann integrable, then it is Lebesgue integrable and the integrals are same. So, whenever such a situation arises, we can use that theorem. So, many of the explicit functions which we deal with in analysis, it is possible to estimate them and see which LP they are in. So, this was only to familiarize you with these spaces, how rich these spaces are and so on. From the next lecture onwards, we will go into somewhat abstract settings again. We will look at what are known as product sigma algebra, and we will also look at polar coordinates on Rn, which will give us some more ways of estimating functions and proving that they are in L1 and so on. Okay.